Imagine pulling up to a charging station in freezing weather and fully recharging your electric vehicle in the exact same time it takes to grab a cup of coffee. For years, that was just a pipe dream, but with BYD's new Megawatt Flash charging system, it's officially a reality. We are talking about going from 10% to 70% in just 5 minutes. If you give it just 4 more minutes, you're at 97%. To put that 1500 kilowatt max charging speed into perspective, this system adds 2 kilometers of range for every single second it's plugged into the car. A quick 5-minute stop on the plug gives you 400 kilometers of real-world driving. This isn't a concept car gimmick either. BYD is actively dropping this second-generation tech into flagship production vehicles like the stunning Denza Z9 GT and the ultra-luxury Yangwang U7, giving them a massive total driving range of over 1,000 kilometers. But hitting a world record 1500 kilowatt charging speed isn't as simple as just turning up a dial. Ultra-fast charging hits a brutal wall governed by the laws of physics and chemistry. To bypass that wall, BYD had to completely rewrite the rulebook on how an EV's entire electrical ecosystem works. To understand why this is such a massive leap, we have to talk about chemistry. Most Western automakers rely on NMC, nickel manganese cobalt batteries, because they hold a ton of energy. But NMC has a major vulnerability: thermal instability. Once temperatures climb high enough to trigger thermal runaway, an NMC pack can catch fire or vent intensely. BYD went a completely different route, using lithium iron phosphate, or LFP. It's cobalt-free, way cheaper, and incredibly stable. But traditionally, LFP didn't hold enough energy. BYD's fix was pure structural genius, using a cell-to-pack layout. Instead of packing cells into modules and modules into a big, heavy box, which wastes massive amounts of space, they eliminated the modules entirely. They turned the cells into long, thin structural blades that slot right into the battery tray to act as a structural honeycomb, boosting the pack's internal volume utilization to over 60%. What's wild is that with Blade Battery 2.0, they actually split the hardware into 2 different physical layouts to close the energy density gap. There's the classic long blade measuring 960 millimeters, which acts as the ultimate long-range energy specialist for flagship sedans, but they also engineered a short blade coming in at around 500 millimeters, specifically optimized for high-power throughput and plug-in hybrids. BYD refined the cathode structure to increase cell-level energy density to an impressive 210 watt-hours per kilogram, moving the platform to a higher 3.8-volt baseline. Industry reports suggest they paired this with a silicon-enhanced composite anode to handle the massive influx of energy. Since silicon expands like crazy when it charges, BYD protects it with advanced nano coatings and high-elasticity binders so it doesn't degrade over time. But here is where the engineering gets tricky. Shoving massive amounts of power into a battery creates extreme heat. Think of it this way: power equals voltage times current. To hit a 1.5 megawatt charging peak on a standard 400-volt car, you'd have to push thousands of amps through the wires. The cables would literally melt from the current. BYD's fix: they built a full-domain 1,000-volt high-voltage architecture. By doubling the voltage, they drastically cut down the current needed to deliver the same power. This keeps the internal cables thin, drops heat loss, and lets the car pull a blistering 10C charging rate, meaning the battery can accept energy at 10 times its total capacity. But even with high voltage, you run into a chemical speed limit called lithium plating. When you force energy into a battery this fast, lithium ions rush from the cathode to the anode faster than the graphite can actually absorb them. It creates a microscopic traffic jam. The ions back up, turning into metallic lithium on the surface. This ruins your battery capacity and causes internal short circuits. BYD bypassed this with a system they call Flash Pass. They re-engineered the anode with high-speed vertical ionic channels, giving the ions a direct highway into the material.
Then they added an AI-designed flash flow electrolyte with a gradient concentration to supercharge ion mobility, cutting internal resistance in half and letting the ions melt smoothly into the anode without ever backing up. Then there's winter. Freezing temperatures make electrolytes thick and sluggish. A normal LFP battery can lose up to 45% of its range in extreme cold, and fast charging completely slows to a crawl. BYD uses an internal AC self-heating strategy that warms the cells far faster than traditional methods. Instead of using slow, heavy electric heating pads under the battery, the car actually uses its own electric motor stator windings and inverter to oscillate a high-frequency, alternating current pulsing at 500 Hz directly through the battery cells. The battery's own internal resistance warms it from the inside out, heating the core from -20 degrees to freezing zero in just 365 seconds. Because of this, even if the car has been sitting in a -30-degree blizzard for 24 hours, it can still charge from 20% to 97% in just 12 minutes. That's barely 3 minutes slower than a perfect summer day. And to cool it back down during hot summer fast charging, Blade 2.0 uses a direct refrigerant 3D dual-plane cooling system that pumps the car's actual air conditioning refrigerant across the top and bottom of the pack, greatly improving cooling efficiency. Now, pulling 1,500 kilowatts into a single car would normally cause a total blackout in a local neighborhood. To save the grid, BYD builds energy storage systems right into their charging stations. These stations have massive built-in battery buffer banks. They slowly sip power from the city grid at a steady, safe rate all day. But when you pull up, the station dumps that pre-stored energy straight into your car all at once. The grid never even feels it. Additionally, carrying cables meant for this kind of power is normally too heavy for a human. BYD solved this by deploying an official motorized zero-gravity dispenser. Because the thick liquid-cooled cable hangs from an overhead pulley on a sliding T-shaped rail, it can slide left or right to meet your car's charge port perfectly, reducing the physical weight in your hand to less than 2 kilograms, so anyone can plug in effortlessly with one hand. But what happens if you're stuck at an older standard public charger that doesn't have a 1,000-volt capabilities? BYD covered that too, with their dual-gun fast charging tech. The car literally has 2 separate charging ports. You pull up, grab 2 completely separate charging cables from the station, and plug them both in at the same time. The car's onboard controller automatically merges the current, slashing your wait time by up to 50% on older infrastructure. With all this speed, did they sacrifice safety? Not even close. While many standard NMC cells experience thermal runaway under extreme puncture stress, the original Blade battery didn't even smoke. Its surface stayed under 60 degrees. But for Blade 2.0, BYD executed what engineers call the impossible test. They subjected the battery to a violent 10C flash charge and immediately drove a nail right through it while it was under maximum electrical load. The result? Absolutely nothing. Zero fire, zero smoke, and temperatures stayed safely below 60 degrees. Even better, Blade 2.0 is rated for 4,000 to 6,000 full charge cycles. Depending on your driving habits, this battery can easily outlast the car itself, providing roughly 15 years of reliable service and potentially supporting over 1 million kilometers of driving before showing any major wear. By solving the physics of extreme heat, freezing winter degradation, lithium plating, and grid overload, BYD hasn't just upgraded the battery, they have officially made charging an EV as fast, painless, and convenient as filling up a tank of gas. Let me know in the comments, is a 5-minute charge enough to make you finally ditch internal combustion? This is for this video. I hope you enjoyed it, and as always, thanks for watching.